Module 10, Lesson 5 covers the concept of outliers, and in short, an outlier is a value that sits way far away from everything else in the data set. And there's actually mathematical definitions for outliers too, where you have to prove it with math. I'm not sure which one we're going to be using today. We're going to find out. According to our pacing guide, it says it's going to take 90 minutes to complete this lesson, but there's only 9 slides in it, so we're going to have to see if they're accurate about that. Florida and Illinois are the 4th and 5th most populous states in the United States. Illinois' largest city is Chicago with a population of 2.7 million people. The 5th largest city is Naperville with 147,000 people. Florida's largest city, meanwhile, is Jacksonville, which is 868,000 people, and the 5th largest city in St. Petersburg is St. Petersburg, which is 261,000. So while the biggest city in Florida may not be as large as the biggest city in Illinois, the 5th largest city in Florida is about twice the size as the 5th largest city in Illinois. So it all kind of seems to balance out there. The populations rounded to the nearest 1,000 of the 5 cities are shown. What does the population of Chicago, the largest city, do to affect the rest of the data in the set? Well, you can see Chicago is just so large, so many people live there. Why you would want to live in Chicago, I don't know. They seem to like shooting each other there a lot. But it's so large that Chicago becomes an outlier. It's so far away from all the other populations for the large cities in Illinois that it just really separates itself from the rest of them. That would be a good example of an outlier. Our textbook defines an outlier as a data value that is very far away from the other data values. So that's going to be the vague definition of an outlier, which I like, not the mathematically precise definition. It says it can be much greater in value or much less in value than the other values. Consider the data shown. How do you know if the extreme values of 225 and 780 are going to be considered outliers? Well, to find out that, we're going to move on to the mathematical definition of outlier. And it says an outlier is defined as a value that lies more than 1.5 times the interquartile range, either above Q3 or below Q1. And we're going to highlight that because that's really important. That is what I expect we're going to be using in class today. Now we're going to move through some slides here to find out whether or not the 225 and the 180 qualify as outliers. To do that, we have the Q1, otherwise known as your lower quartile, is being 300. Your upper quartile, or Q3, that's going to be 425. The interquartile range, that's the difference, 475 minus 300, that gives you an interquartile range of 175. Now we have to take that 175 and we have to multiply that value by 1.5. So the Q3 value, which was 475 times 1.5 is plus 1.5 times that interquartile range. Well, 1.5 times the interquartile range is going to be 262.5. And when you add that 262.5 to the 475, that means that the value would have to be 737 or greater to qualify as an outlier. What was the number we were looking at in our data set? 780 right there. 780 is greater than 737, so it does qualify as an outlier. Now for Q1, we're looking for the lower limit. We're going to take and multiply the 1.5 times the interquartile range again, which gives us the same 262.5, and then we're going to subtract that from the Q1 value, the first quartile. When we do that, we get 37.5. So for the bottom number to be an outlier, it has to be less than or equal to 37.5. Come back up here, what was it? It was 225. 225 does not count as an outlier, but 780 does. Now this is a brand new piece of information to me here. It says for a box plot, also known as a box and whisker plot, here we represent the data set, and on the box plot the outliers are indicated with an asterisk. So you notice this right hand whisker, it doesn't go all the way to the outlier. It only goes to that number that is still inside the range of not being an outlier. And then the outlier way over here, they put an asterisk on it because they don't want to skew all the other data they have involved when using the box and whisker plot. Let's take a look at some real-world problems involving outliers.
In an upcoming election, there are 7 candidates running for an open seat in the local city council. The candidates' ages vary from 23 to 72 years of age. Are any of these values outliers to the data set?
Well, okay, that was pretty vague. Let's see what they want us to do with that. Nothing exciting there, so let's scroll on to the next slide. The ages of the candidate in years are listed right here. First thing we're going to do is we're going to put them in order from least to greatest. So I've got a 23 is my least, 72 is my greatest. Then we've got, let's see here, 48, 49, 55, 57, and 63. Those answers check. Now let's see what else we have. So find our quartiles in the inner quartile range. Well, we've got 1, 2, 3, 4, 5, 6, 7. That means 55 is going to be the median, the middle number. And then if we take right here, 48 is going to be my lower quartile. And the middle of the upper half is going to be 63. 63 is going to be the upper quartile, and then my inner quartile range, that's going to be 63 minus 48, which is going to be 12, 15, I believe, if I did that right in my head. All of that checked. So now I've got my inner quartile range, I've got my lower quartile, my medium, and my upper quartile. From here, we're going to move through the steps to find out if either of the n numbers are going to fall into the outlier category. So, first thing we're going to look at with our Q1 times the inner quartile range. Well, the Q1, was equal to 48. Q3 is what we're looking for. That was equal to 63. You can see that listed right here. So we have our Q3, which is 63, and 63 plus 1.5 times 15. Well, that's going to be 63. It's going to go right there. And just for time's sake, let's go ahead and grab ourselves a little 1.5 times 15 this way, which is going to give me 22.5. That adds up to be 60, 70, 85.5 is what we would need to have a number greater than or equal to in order to qualify as a outlier. If you take a look at the age of the oldest person was 72. Is 72 going to be an outlier? No, he's not. He's just going to be right there in the group with everybody else. The lower quartile, though, we may have an issue here because there's not too many 23-year-olds that run for office. So we're going to take that 23-year-old, and we get that 48 right here. The 48 comes from this value, which is going to be our lower quartile. Let's go ahead and highlight that as well. And we're going to take that and say now we have 48 times, we're going to have the same 22.5 for our 1.5 times 15, which is that 1.5 times the inner quartile range. When we do that and subtract it, let's see, that's going to give me 25.5, I think, if I did that right in my head. Check that. It does check. So for the lower end to be a outlier, it has to be less than or equal to that 25.5. The youngest person there was 23. 23 is going to be less than 25.5. So the 23-year-old running for office, that person qualifies as an outlier. The 72-year-old, just another old fella trying to get himself elected. Now we can move on to our next slide to answer the questions. Look at the ages of the candidates. Are there anybody less than 25.5? The answer is yes. And since we had a yes there, we're going to take and say, what is that person's age? That person's age was 23. And we're going to click yet good again. Move on to the next. Is there anyone greater than 85.5? The answer is no. And that means that 23 is going to be the outlier, and it's going to be the only outlier in this data set. Now it's going to be time for you to pause the video, work extra example 1, and find out which, if any of these, qualify as an outlier. For this problem, they gave us the numbers 60, 55, 75, 52, 60, 50, and 51. And of course, the first thing that we need to do is we need to place them in order from least to greatest. So the least number is going to become 50. After 50, I get 51. Oops. After 51, I have 52. Then I have a 55. Then I have a 60. Then I have another 60. And then I have 75. When we count out our values, we have 1, 2, 3, 4, 5, 6, 7 members of our data set. That means that my median is going to be 55. My lower quartile, the middle of the lower half, is going to be 51, and my upper quartile, the middle of the upper half, is going to be 60. So, for doing our Q1 to find out whether or not we have got a lower outlier, we're going to take our Q1 plus 1.5 times our interquartile range. Our interquartile range is, of course, going to be the 60 minus the 51, which is equal to 9. So my Q1 is going to be 51 plus 1.5 times 9, which means I'm going to have 51 plus, that's going to give me 9 plus 4.5, which is 13.5. Actually, that shouldn't be plus, that should be minus for the Q1. So let me take and change all those plus signs to minuses, because we're looking for numbers less than that, which means that my for it to be an outlier for the lower half, it's going to have to be a number less than, let's do some subtraction here, 51 minus 13.5, do some borrowing, 10 minus 5 is 5, 10 minus 3 is 7, 4 minus 1 is 3, so it would have to be a number less than 37.5. There are no numbers in our data set that are less than 37.5, so we know we do not have any outliers on the lower end of the data. But what about the upper end of the data? Let's take a look at that. Now we're going to stop and look for the upper quartile outlier, and the upper quartile's value was 60, so for that one we're going to have the formula is going to be Q3 plus 1.5 times your interquartile range, where our Q3 value was 60, plus 1.5 times the interquartile range we found earlier was 9, which means that we're going to have the 60 plus, and the 1.5 times 9, that was our 13.5, which gives us a answer of 73.5. So, if we have any data values that are greater than 73.5, those are going to be an outlier, and we do indeed have one of them right there. 75 is going to be the only outlier in this data set. Now we're going to jump back over here, select 75, hit check answer, and the answer checks. This right here, folks, that's going to be showing your work. That's what I've got to see in order for you to get full credit for doing these problems. Now this is where we're going to end part 1 of this video. When you come back for part 2, we're going to learn about mean, median, and outliers and how all those things affect each other. See you in part 2.